Thank you.
Good afternoon. The automated Megacam data quality assessment with machine learning is the title of my presentation. In fact, we have a different machine learning project in CADC. The quality assessment of images is one of them to help users. We have different images in our web page, bad and good. Long story short, we want to give users more options to select better images. If an image is bad, we can suggest that it's bad, don't bother yourself, don't download it because it's very big. This project is a supervised problem, and I will try to give you a big picture of the target and the input data that we have used to train machine learning models. I'm not going to describe the models, just mostly about the input and output. For many years in CADC, the Megacam images were classified into different classes by Stephen Gwen. Thanks to his efforts, we have very nice training set like this. We have images with quality. So we have lots of good images, as well as bad tracking, really bad tracking, short exposure, dead CCD, for example, terrible seeing. And since we have lots of images, 1 million images, about 14 million CCDs, I was asked to find a machine learning solution to separate good from the bad one. It seems that it's a binary classification, but it actually is multi-class classification, that I'm going to describe that. And for getting better training set, we double-check to find possible human error in the training set. Okay, what does a Megacam image look like? This monster, very big. So 36 CCD in one image. Even one CCD is big enough for the machine learning project. So we wanted to find a solution to solve this problem. We didn't want to downsize the images because bad information was necessary for us. So we didn't want to kill information. Okay, 1, 2, or 3 example of traditional method for labeling images in CADC by Stephen. Because the exposure is very big, we cannot download each time and see 36 different CCDs. So Stephen randomly selected one part of one CCD like this, and then he's expert and say, oh, it is good based on some experiments. So another exposure similar but is not. When you go in details, you can see that it's a really bad tracking. So we should inspect closely. And another example, if the window comes in this area, we could label this image like bad. We cannot see all the image, just one part. If this part is good, so we double check to make sure that we have good training set. After this, we have our training set. We know what we want. Different background problem, bad seeing, really bad tracking, lots of good images, and with dead CCD. We know what we want. Now I'm going to describe our input data. Okay. At least for a newcomer to this area, if I ask them to classify and label an image, they select some objects in CCD and go into details and inspect the shape and a background estimation, rough background estimation, and then say, okay, it's good or bad. For example, in this case, one class of this object, the second class, and the third. We can cluster this data into, for example, 20 clusters or 10 clusters. It depends on the nature of the problem that we are going to solve. Okay, we can do these steps by machine. When we get more experience, as if we can make a space of our experience with different components. Like we can recognize the galaxies, we can recognize stars, low background fluctuations, some saturated stars. So we complete this space with the component that we know. And for one image like this, we say, okay, we have stars, we have good galaxies, low background fluctuation, low noise, so it is good. If we come to this, we have only one component, weird objects. So we don't have to inspect all of these objects. Some of one or two of them is enough, and we can have some statistical information of the image. And this is another example. This is bad. This is our experience. We want to use this method to train a machine. We can select the object by source extractor. We can find the electricity, the shape, the big. It is big or small. We can use a self-organizing map to cluster the input. I have introduced two papers in this respect. We can choose 20 clusters, 10 clusters. It is optional, and we know the number of the similar object in each cluster. So instead of using whole CCD, we can cluster the data in the CCD into 20 different clusters and pick only one representative of each cluster, something like this. Okay, this is an example. We have a CCD, we run source extractor on this image and send the output of the source extractor to a sum map. Then cluster the data and pick up only one object from each cluster. The result is this. So, for example, in cluster 1 here, we have images like this, 19 similar images to this. In cluster 20, we have 40 very similar to this. So instead of using the CCD, big CCD, we can use this representative. Okay, another example, very bad tracking. Here, for example, we have more than 200 objects like this in the image. So now, this is our input, very big. Instead of giving this to machine, we change it to this. And we have information of pixels, we have statistical information taken from some, not from source SE, because we have obtained this statistical information from self-organizing map, 800 times smaller. So even you don't need GPU to process the data. Okay, and to an example, good and really bad tracking. This is like DNA code. This is actually fingerprints of telescope in different conditions. So we can interpret this data, but we want to leave it to machine find the details. Each image like this has one table taken from SOM, or self-organizing map. Okay, this is the top line we have in our CADC. I'm going to explain what's going on here. So we have we give the number image ID of the image, and then the only option we have here to select. We want 20 clusters, we want 10 clusters, or 30 clusters. This is the only option you have to choose here. For 20 clusters, for example, we send data from source extractor to SOM. We have a distribution of data on SOM. We have a feedback from the SOM to image, and we can cut out the image and send it to as first input. We have input from self-organizing map as statistical information, and this is our input data. We have now a deep network and with two inputs. The main input is the CCD. The second input we can inject somewhere in between the layers as a auxiliary data. The result is this, and this is output of our network. Okay, About the training steps, when we have input, when we have our targets, when we know what we want, when we have something to predict, then we put a model between and make a different connection between the input and output. When we do that, as if we are making a parameter space, something like that. And we always start from somewhere, initialization, and to go to find the deepest part in this curve. If we are lucky, we can find the solution easily. If not, we could end up with local minimum like this, and we can add some term to our optimizer, like gradient, stochastic gradient descent, to get rid of this local minimum, so we can find the global minimum. Here we have to check model. This is fine-tune steps. We have to make sure that we have find the best model, and we can, when we make sure that we are in the best place, we are done, and we can say that we have a trained network. And it is important to know that this is not very complicated data. We can use not very complicated model or data. So it is the difference between the very complicated model or data and the less complicated one. Okay, there are some results here. This is the ID number. You can search for this ID. What you could see is this. And the prediction is background problem, 98%. Here another one, good, 99%. And another, this is tricky because it's originally labeled by bad. However, it is good. And the prediction of machine is this, 93% good with 1 dead CCD. This is prediction of machine. Okay, here's very interesting because a combination of two cases. The machine could detect every small bad traction, bad track in the image and observation, 29%. It is a little bad tracking there, but mostly is bad sync. So combination of that. And here you can see that machine predict that this image is really bad tracking. Okay, we are using the model in CADC. More than 200,000 images, 9 million CCD were checked in less than 1 day by this method. And we have about 800,000 that we are going to test. We independently gave different results to different people, 5 different sets to different people, and independently check the result. It is test. It is not validation. It's a test sample, and we got about more than 97% accuracy. And thank you for your attention.